ඕකේ මුලින්ම ඔයගොල්ලෝ දැන් ඕකේ මුලින්ම ඔයගොල්ලන්ට ඔය හිතන්න ඇත්තේ vector valued functions කියලා. මම හිතන ඔයගොල්ලන්ගේ functions ගැන මම වීඩියෝ එකක් කරා YouTube එකේ. ඔයගොල්ලෝ දැක්කඩා functions කියන්නේ මොනවා වගේද කියලා මට නිකන් තරහදාසක් දෙන්න function එකක් කියන්නේ මොකක්ද කියලා. මොකද ඒක ලොකු අදහසක් නැත්තම් සාමාන්‍ය function එකක් කියන්නේ මෙහෙම සීන් එකක් නේ. මේ function එකක් තියෙනවා. ඔයගොල්ලෝ මොකක් හරි කෙනෙක්ව input එකක් දෙනවා. මොකක් හරි function value එකක් එළියට ගන්නවා. එතකොට මට වෙන්න පුළුවන් මම x සහ fx ට වෙන්න පුළුවන් ආකාර ගත්තොත් දැන් බලන්න මේ ඇයි හිතලා මේ කැල්කියුලස් කියලා එකක් එන්නේ කියලා. එතන මේ ගත්තොත් මෙයා ඔයාට x කියන එක තාත්වික නම් එක සංඛ්‍යාවක් වෙලා fx කියන එක තාත්වික සංඛ්‍යාවක් වෙන්න පුළුවන්. මේ වගේ අපිට real to real functions. එහෙම නැත්නම් ඔයාට x කියන එක වෙක්ටර් එකක් වෙන්න පුළුවන්. මොකක් හරි වෙක්ටර් ස්පේස් එක. අපි සාමාන්‍යයෙන් i to the r කියන එක්කෙනාගේ n කියලා දානවා components n ගානක් තියෙන වෙක්ටර් එකක්. ඒ කියන්නේ ඔයාගේ එයාගේ dimension එකට n වෙන වෙක්ටර් ස්පේස් එක. එහෙම එකක ඉඳන් ඔයාලට තාත්වික සංඛ්‍යාවකට යන්න පුළුවන්. දැන් මේ වගේ වට අපි කියනවා multi variable functions. සාමාන්‍ය නම ඒ කියන්නේ ඔයාගේ inputs ගොඩක් තියෙනවා. ඒ කියන්නේ අපි fx කියන ගත්තොත් ඔයාලට inputs ගාන මෙහෙම n ගානක් තියෙනවා. හැබැයි ඔයාගේ output එක තාත්වික සංඛ්‍යාවක්. මේකට අපි කියන multi variable functions. ඔයාලට සාමාන්‍යයෙන් ඔයාලට multi variable calculus වල මේ දේවල් ගැන ගොඩක් ඉගෙන ගන්න. ඊට පස්සේ ආයෙ තියෙනවා ඔයාලට පුළුවන් real number එකක ඉඳන් ඔයාලට වෙක්ටර් එකකට යන්න පුළුවන්. මේ වගේ වෙන්නේ වෙක්ටර් valued function කියලා. උදාහරණයක් විදිහට යම් කිසි තැනක ප්‍රවේගය වගේ ගත්තොත් ඔයා කාලයත් එක්ක ප්‍රවේගය කියන්නේ වෙක්ටර් එකක්. කාලයත් එක්ක ප්‍රවේගය වෙනස් වුණාට ප්‍රවේගය වෙක්ටර් එකක් නිසා කාලය කියන්නේ ස්කේල් එකක්. ඒතර වගේ ප්‍රවේගය ගත්තොත් කාලයත් එක්ක ප්‍රවේගය කියන්නේ වෙක්ටර් එකක්. ඒතරට අවුට්පුට් එක විදිහට හම්බෙන්නේ වෙක්ටර් එකක්. හැබැයි ඔයා ඉන්පුට් එක විදිහට දෙන්නේ ටයිම් එක විතරයි. ඒ කියන්නේ ස්කේල් එක. ඊට පස්සේ ඕගොල්ලෝ ගත්තොත් තව ජාතික ෆන්ක්ෂන් සෙට් එකක් තියෙන පුළුවන්. ඔයාගේ ඉන්පුට් එක වෙක්ටර් එකක් වෙලා අවුට්පුට් එක වෙක්ටර් එකක් වෙනවා. මේ වගේ ඒවට සාමාන්‍ය කියන්නේ වෙක්ටර් ඉන්පුට් එකකට වෙක්ටර් එකකට නම් ලොකු නමක් නමක ලොකු ඩවුන්ලෝඩ් එන්නේ නැහැ. නමුත් ওই ටික තමයි බේසිකලි තියෙන නම්බර් සෙට් එක. කියන්නේ ෆන්ක්ෂන්ස් තියෙන පුළුවන් විදිය. එතකොට මේවට කවුරුහරි කියන පොඩ්ඩක් මේ is there any Tamil students or anyone who can't understand Sinhala please put me a chat message or raise a hand. I will continue in English. Okay. So if there is anyone like that, please let me know. Okay. So I can continue in English too. Okay. So then you can let me know. So I will continue. So otherwise I will continue in Sinhala. Right? So okay. So is there anyone? So please, if you can't continue in Sinhala or you need to explain it in English, please let me know. Right? So then I can arrange according to that. Otherwise, I will have I have continued with Sinhala, right? Because most of them are Sinhala. So is there anyone? Please. Yeah, somebody had unmuted the mic. So. Anyone? Okay, so department reps, I think there are reps of the department. So if you have any problem, so you can message one to the reps and they can message to me. Right? Okay. So I just recommend that there are 4 types of functions and like if there just in case, right? Is there anyone who is can't understand Sinhala? So 4 types of functions. One is you can give variable as a scalar and you get a function value as a scalar. Second type is you can get a variable as a vector and function value as a scalar. And third one is you can give the variable as a scalar and your function value as a vector. And other thing is you get a variable as a vector and you get a function value as a vector. Okay. So then it's better to continue in English. It's familiar to me. Okay. So then if you take this thing, right? This guy. This thing we call vector value function. Right? It means if you take this is a vector function means your function value itself is a vector. Right? So basically this is the one we like considering in the first part of vector. So this is also you can take it as a vector value function, right? Because your function value itself is a vector. So basically this is the function type you will consider at first in your at the start, right? You get RT and argument and so on. This is the type you contain because your input is a scalar and output is a vector. So this is actually this is also a vector value function in the fourth type of functions, but this is the type you considering in your course, right? So this is then we need to analyze these functions. We cannot use we can use actually the concept we derive for the real-to-real function as we did in our A levels and so on, but we cannot use them directly. Okay, so then, so let's hold on a moment and let's look back what we know about our real-to-real function. Let's say you have some function like this x, and you have fx, and you know if you draw a tangent line to some point, right? The tangent line, the gradient or slope of this line is given by your derivative, right? dy over dx, or simply f dash x, right? If this function is fx. So this is what we know for a scalar value or real-to-real functions that we learn from A levels. But when it comes to like what you call, when we comes into vector valued functions, you have something like this, right? So you have, is it y x? Please forgive me about my drawing. So you get some something like this, okay? So at each of the thing, you it is, let's say it is a path of some particle or something in the space. So you can denote the position of each particle at each time instant as RT, right? You can write RT as something like this. XT, YT, ZT. It means it is nothing but if you know you can in Cartesian space you can denote any point of the Cartesian space like X, Y, Z coordinate. But in this moment, what will happen is your both X coordinate, Y coordinate, Z coordinate is varying with the time, right? It is not constant. Previously, you have constant coordinates when we do vector geometry first semester and so on. But now your coordinates is changing with the time, right? So then this is itself become a vector valued function. Okay. The thing is, this thing is a vector valued function because this is a vector and your input is t. When your t is changing, your time is changing, this vector is changing. So this is a vector valued function. Okay. So now, if I ask, what is the gradient of this function? Or if I want to differentiate this, right? Because if this is a function of variable t, I should be able to differentiate this function. How to differentiate this thing? Like this is like somewhat tricky problem, right? So you can differentiate it definitely. You have some definition, but you have some way to differentiate. How you should differentiate it? So actually, we previously actually we have some function like let's say fx equals x squared or something. We know how to derive it. Like if that's x, we know 2x, right? It's a real function. Now we have a vector. The thing we do is since these are vector valued functions, okay? Since these are vector valued functions, we differentiate each of these with respect to t. Okay. So we take it is equal to x dash t times y dash t to z dash t. So now what does this mean? It means we say, okay, the derivative is, these are the real functions. So simply write it as a vector and your first component is differentiate this xt, and the second thing is differentiate yt, and third component is differentiate zt, no? Zt, right? I cannot pronounce exactly how this is, right? So then if it is the vector, okay, what does this mean? What does this vector value, oh, my r dash t means? Okay, what does this mean? Note that this thing, let's say I can consider it this way. I keep this thing is constant, right? I keep my y coordinate and z coordinate is constant. So this x dash t or derivative xt means how much rate of changing I have along this direction. And this my y dash t means how much change I have or how much rate of change I have along this y direction. And this thing means how much change I move along z direction. Okay, so it is just a velocity in terms of directions, right? If you have three directions, x, y, and z, because you have 3D, you are considering it 3D. So you have three directions. In each of the directions, you have velocities in each of the directions, in x direction and also in y direction and also in z direction. Okay, so then you can get the velocity vector like this. Okay, you call this as a like you can think of, if it is a position of a particle, you can think of as a velocity. Okay, so then what you can say about this thing, right? What you can say about this thing? Let's say I would take as this thing is like r dash t. Let's say what you can take about this component r dash t magnitude. What can you say about this? You take your derivative and you divide it by the norm, or just like if you have your norm is nothing but you have some vector, let's say ABC vector, it's 3 component vector. Your norm is nothing but a squared plus b squared plus c squared, right? This we call L2 norm, right? There are infinite number of norms. You can have many number of norms. So you have some component vector like an, and you have some your n norm like sigma I squared 1 to n ai p, and you to get the power of 1 over p, you can take this LP norm, right? You can define many number of norms because this is L2 norm because you have the power of 2, right? And you get the square root. So actually you will learn this in your module linear algebra, basically. So just in this case, actually it is enough to know this L2 norm, right? So this is L2 norm. So this like L2 norm is normal how you define the length between 2 points in space, right? You know how to get the distance between 2 points. So then this is actually we call this is a tangent vector. Why this is become a tangent vector? Because if you draw a tangent line, right? If you draw a tangent line, this vector, this derivative vector, give the direction for that tangent vector. Okay, give the direction. But the problem is this is magnitude is varying, right? Because in some places you can have this magnitude is pretty much high. But if you want the direction of the magnitude or direction of the your tangent, what you have to do, you get your r dash t and divide it by its magnitude. Then you know it any point what is this curve is heading. In this case, you can have some tangent vector like something like this. Okay. In this case, you can have tangent vector like something this. When you divide by your magnitude or your norm, what will you get? Eventually get is only the direction where your curve is heading. That is why we call it a tangent vector. Okay, you can draw a line and you can get a tangent vector. Then you know this is a unit magnitude vector. Then what you can do it is t dash t. You get t dash t divided by t dash t's magnitude. Okay. Actually, eventually you can get this thing t dash t. Okay, t dash t. So t dash t, and this is actually derivative of a tangent vector. Okay. So if you get this thing t dash t over t dash t's magnitude, what does this mean? Or what does this mean? So this tangent vector's derivative, it means that if you, let's say you have only a direction, that you have magnitude 1 and you have some certain direction. So you know your magnitude is constant, your magnitude cannot change. But if a t dash t means how much this tangent vector direction can change, it means it can go along, rotate to this direction or into like to up from the screen, or you're up inside to the screen, it can change anywhere. So the normal vector, we call this thing as a normal vector. This is a measure how your direction of your tangent vector is changed. Right? This is also a magnitude of 1. So then you define your binomial vector as this nt. This we call binomial vector. This is actually measure of, let's say you have something like this. Let's say you have some curve, something like this. Some curve at some moment, it goes in this direction in my plane of the screen. And the next time instant, it will go in this direction. Okay. So it means it changed its direction to some delta theta angle, right? To in the very next movement. It means its motion is already containing in the plane of my screen. But this binomial vector is a measure of how this plane can change. How this plane can move upward my screen or downward to my screen. Or this plane can also, it can be rotate around my screen or anything. So this is actually this is the movement of a plane, right? Because if you get some, if sometime it is going into this direction and it is likely to rotate in this direction, it means its movement is already contained in the plane of the screen. But binomial vector, this guy is a measure of how much this plane can change. Okay. So then you have many number of like equations and so on. That's the basic idea. Tangent vector is your direction. Basically, this is your direction, right? This is a direction of a particular point. How is your curve is directed, and this thing is actually how your direction is changing how direction is changing, right? And this thing is how your plane is changing. This plane means how is your, because if you know your direction and you know how your direction is changing, you know what is the plane your particle is going to move. But binomial vector is measure of how much it how much is tend to change its movement on the plane, right? It means it is, let's say you can think of it like way you can move some particle, so and you move it in certain direction and you change in to some direction, right? It means that if you move first, you move in this direction and you move to in this direction. It means if any movement is this delta t time period, its movement is contained in this plane, the plane of the screen. But this binomial vector is measure of how much that plane is going to move. If it is going to rotate or if it is going to, anyway, it is going to rotate. It is how it's going to that angle or slope of this plane going to change. Okay. So is that clear, that idea? Or anything need to be explained? Hello? 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 Anything don't need to explain? Or is it clear? Hello? Anything to explain? Hello? Okay. So then something like this. Now, let's say I will take, for sake of easiness, I will take only XY axis because otherwise 3D is going to be not much complex. So I would get something called RT, which is equivalent to XT YT is my YT, and I know this is my, let's say this T1 and this is T2. I want to find like this length of this curve from T1 to T2. Okay, because this movement is in the, these are the x coordinate. This is the time instant, right? This is my T and this is my T. Okay, this is my when my time equals T1, my particle is here, and then time equals T2, my particle is here. So now I know the path. Now I want to analyze, or I want to get to know what is the total distance my particle is traveled between these time slots. It's T1 and T2. So how I'm going to do? This is, we use something called arc length, right? Okay, arc length. What we are going to do is, actually we integrate r dash t no dt along the path, right? Along T1 to T2, we integrate this thing. Why? You know, I will give it the physical sense, not in the mathematical sense, because you need to get only the difference to do the problem in the paper. Okay. So I will just intuitive idea, then you can actually go through some notes and refer the actual proof. So then let's say you know r dash t. What is r dash t? Is velocity, right? It's velocity because it is how it's position gonna be changed, right? It is what actually it gives the direction and the amount of the magnitude, how much your velocity is there. Because if you r dash t, it has a certain magnitude and it has some direction, right? So it means it gives both the magnitude and the direction of your velocity. But if you just consider this only the magnitude part, you will get the speed, right? It is only a speed, right? Because it has no direction, it's just a scalar. It must guess how much speed it has. So if you get the speed and integrate it over time, what you will get the distance. Okay. What you will get is the distance. Okay. Fine. You got it? Or if you get if you get the if you integrate this thing T1 over T2 and you integrate the velocity, you will end up in everything like actually I don't know displacement, right? You end up in displacement if you integrate the velocity, right? Because it gives how much you go to how much of the direction, right? How much you go to the in certain direction, it will give to you. But if you just consider this velocity, if you just only consider the magnitude of this term, it means if you consider only the speed, you will get the distance. That is why we call this is arc length. Okay. So these things are totally different, right? This thing are totally different, right? Because if you integrate this one, you will get a vector, right? It is actually like equivalent to the displacement. But this thing is equivalent to distance, right? It has no direction. It has only a like value or what you call some sort of magnitude, and it is you go to the distance. Is how much arc length or how much length of the path it travels to between these two time zones. Okay, fine. Oh, you need to another clarification. Hello. If you have a problem, you can ask, right? You can send me WhatsApp, but I think I cannot sure. I can check my phone here and there. So if you have a problem, you can send me to the chat, or you can ask directly from unmute from one. Okay. So that's fine. Now you understand what is the no tangent vector and the normal vector and the binomial vector, and also you can have several other type of equation of that. You can I will send you the notes also, some notes, and you can refer that too. And also in your lecture notes they are given the formulas also there. So having the idea, then you can apply the formula with what is actually going behind it. Okay. So that is it. So this is actually about the vectorial functions. Actually, this thing is only in your notes, and then you have some proofs. And actually, I'm not going to do that, so you can do it by your own. If you encounter any problem, you can contact me. So if you have time, I will disclose to you. So actually, this vectorial function, is it okay, or you need any explanation? Hello, hello, anyone? Okay. Now you are gonna do is something like this. Now we are going to do something like, let's say I start with line intervals, right? Because I will start with line intervals because it is the most easiest part, and then you have to go something in multivariate intervals, and you have areas and so on. So before understanding that, you should understand the simplest case, the line intervals. Okay. So let's say what is the interval list means. Okay. I know we know integration in the advanced level, but most of the time we just do some sort of like it is the opposite side of differentiation, and we memorize some sort of things and just memorize, and we eventually we don't know what is the integration is. That's actually sad truth of our country. So that's why actually most of the time, actually, including me, face some difficulties to understand these concepts, right? So then if you take some function, right, fx. So let's say I would take this integral a to the p fx. What does this integration mean? Okay. So what does this integration means? It means this integration means the area between the curve and my x-axis, okay, between a and b. This area actually this corresponds to this integral. Okay. It means I integrate this function along x for x equals a to x equal to b. It means I integrate from here to here. It means this type of integrals I call line integrals. Actually, this is a part of line integral. It means I integrate this along this line from a to b. This is actually one part of line integral because there is no any other line between a and b. I can only go from a to b along this line. So these type of integrals I call line integral. Okay. It means I take some function and my variable is there and my other point is b is there. I go from here to here. I integrate my function fx dx. Okay. So actually it has a physical meaning. In this sense, you have the area under your curve and x-axis by evaluating this integral. Now let's say you have now you have this line integral. Now you have some other thing, right? Let's say I take actually I have to do 3D figure for this. Forgive me about drawing. It sometimes go missing, right? So let's say you have some function, something like this, okay? Because I cannot go how I do. Let's say you have function like something like this, right? This function is something of type is xy. It means you have each point of xy, you have some function value, okay? Each point of xy, you have some function value, okay? Let's say I write this integral. Okay, so you actually, let's say dr or something. So actually, I will show you how to write this dr. Okay, so don't worry about that. So then actually some sort of dr or some sort of some sort of thing. Let's say let's see how you put this one, right? Let's say you want to integrate this function from here to here, and let's say you put dr. Dr is nothing but your this vector, right? This is a position vector, right? Your r vector. So you sort of some dr. Let's do not worry some dr. Let's put dr as it is, and let's say behind the idea, what is this line integral mean in the multivariable case? Okay. So now you have some point, let's say it is x1 and y1, and you have some another point x2, y2. Okay. So this means you need to integrate from here to here. You need to start from here and you need to end from here. Let's say you have to start from here and you need to end from here. Okay. Now in this multivariable space, or like my two variables in my variable case, how many ways you could have to start from here and end from here? Can someone tell how many ways you can go from, let's say this is point A and this point B? How many ways you can go from A to B? Obviously, you have some ways. This straight line is there, right? You can join this point and you can go there. Any other ways? You can go from here to here. Hello? Any other ways? Hello? Tell me. Any other ways you can go? You can have an infinite number of ways, right? Probably you are thinking is right? Because you can go this, go like this, you can go like this, you can anyway you can go, right? There are infinite ways, right? You have infinite ways. Now is the problem. Now, if you want to define this line integral, right? Prior to define this, you need to define what way you're going to choose, right? Because we don't know it. Because I think there are some functions that part doesn't matter, but that which are we call potential functions, which I come back to later. But the thing is, in this case, without some integrals are, because some integrals are this depend on this path. It means the integral is depend on this the path you choose. So you need some way to define what path you're going to choose. Is it you're going to choose this path, or you're going to choose this path, or you're going to this straight line path? You're going to define. How are you going to define this path? That's the next problem, right? So how are you going to define? So now it is a problem, right? So it means actually these lines are on like xy plane, right? So let's say if I properly draw only xy plane to your reference, let's say my x1 here and y1 here, and your x2 here and your y2 here, and you have to start from here and you need to end from here. So how many ways you can go? Let's say you can have this straight line and you can go in this way and this way and this way. This is like only xy variable plane, right? You can go from the point x1 and y1 to point x2 and y2 in infinite many number of ways. Now, each of these, if you think of that, right? This is a path, right? If this is a path, any single path, let's say let's consider this only this the path I circulate around blue. So in this path, actually you can think of it as a function y equals fx. So each coordinate in this path you can characterize as x into fx. Okay? Fine? Fine? You got it? Hello? You got it? It means in your characterization, because let's say you have some part of like this. Let's say you have pretty much example. Let's say you can get, let's say this is 1 and you get 0, 1, 0, and you have to go through 2, 4. Okay. So then actually to 1, 0, let's say, so let's say you have to go 2, 3, right? Okay. So then you will take the curve. Let's say this curve, I can, let's say x squared minus 1. If x squared minus 1 is there, what you have x equal 1, you have 1, and x equal 2, you have 3. Okay. So then any place of this curve, your xy coordinate, you can, let's say this is x and this is y. You can simply put as y equals x squared minus 1. Now we are every coordinate in this curve you can represent as x times x squared minus 1. This is your curve. Okay, fine. Fine. Hello. Fine.
Yes.
Now, if you want that some integral fxy, right? You go to x1 and y1 to x2, y2. Now you put some dr or something here, because I just put here because you need to some sort of like dx or dy or something here to integrate, right? So this thing you understand when I talk about volume integrals and so on, what this dr thing is. That's why I'm not going to discuss this here. So now you can write this integral as something like this. Let's say you can write f x, and you put in terms of y, you put some function times dx, right? Now what will happen? You can put x 1 to x2 dx. Because you need only to vary dx, because according to your x, your y is automatically varying. It means if you get your xy plane, right? Your xy plane, you start from here, x1 and y1, and you end up here, x2, this x2 and y2. Let's say this x1, y1, and this x2, y2. Okay. So you start from here, you go from like this, some sort of curve. This curve is characterized as y equals some sort of dx. Okay. So it means you move x to here. Okay. X from here to here. What will happen? Your y coordinate is automatically move from here to here, because you know the relation between y and x. It means though it seemed to be as a double integral involving two variables x and y, we can reduce to integral incorporating one variable. This is why we call this a line integrals. Always you can remember that you can use these line integrals using only one variable. Of course, you can evaluate in using two variables. That's fine. I think you cannot evaluate it to two variables because it is a line. So you need to get to one variable. If you properly characterize your curve, you can end up with a single variable is a line integral, and you can integrate it. Okay, fine. Good. How will it go? So then, depending on this, you can find the relation between x and y. Now you can say what is your starting x point is, what is your starting end point is. You can write this integral, or else you can write this as y1 to y2, and you write this as some sort of hy into y, right? dy. So but in this case, what you do, you put some you write your x in terms of y, because if there's a line means we have some relation between x and y. Okay. If you are able to find that relation, you can convert this into a like typical integration you know from the A levels. Okay. So let's say I will take some example. Let's say I will get some fx y is equal to 2x plus 1. Okay. 2x plus 1. Okay. Wait a minute. I already write on my screen. Now it is coming. Okay. So now 2x plus 1. So then I need to integrate this from, so it's a 0 to 1 to, let's say I want to integrate in or 0 to 0 to be simple. I want to integrate from 0 to 1 from 1 to 1, right? Along this path, along this line. It means that I have my xy plane. So it is 0 to 0. Okay, so 0 to 0, you can have something like this. Okay, and you need to integrate from 1 to 1, right? And my chosen curve is y equal x square. Okay. So then I can write this integration as like this. Okay. I can write this integration as my x is going to 0 to 1. Okay. 0 to 1. My fxy is 2x. In terms of y, I put x squared dx. And you can write simply evaluate this integral, right? You know how this evaluate this integral in your A levels, right? So this is actually equal to 0 to 1 2x dx plus 0 to 1 x squared dx. So then you can write it is x squared plus x cube divided by 3, and you can put 0 to 1, and you can get this integral as actually 1 plus 1 over 3. It is equal to 4 over 3. Okay, simple as that. Okay, I think hope it is clear, right? It is not much, right? It's a very simple thing, right? You get the function and you find the relation of your path related to, because in this case, if you when you take in this path, this is not more a function of a two variable. It's already become a function of one variable, because if you have if you're moving x along this direction, if you have some x value, you cannot have an arbitrary y value. Your y value is fixed with your x value, right? If you have some x value x naught, you should have x naught squared as your y value. So your function is no more a two variable function. It reduced to one variable function. It means you can write your integral as this. Okay, fine. Hello, fine. Or anything you need to clarify about this?
No, yeah.
Okay, so I think hope it is clear. So now WhatsApp call करने बाबा making apa? ये kawan WhatsApp call कर. मैं अरे ඊට පස්සේ okay, so then we need to move on. Like now it is some line integrals, right? Now let's say we need to have some sort of some bigger sense, right? So we need to have some sort of like now we are going to some desperately we go into some called what you call into our double integrals. Right? So double integrals in the sense that now we are going into the first, right? Double integral is something like this. It is fxy dx dy. Okay, it is some you have some y1 to y2 and x2 to y2, x2 to x1 to x2. Okay, x1 to x2. You go somewhere here. Okay. Okay. So now you are going to some place of here to here. Okay. So then, so now is the thing is different, right? I already know the vector plane. Okay. Yeah, you can take any line, but because what is the curve in this previous problem? Somebody asking why you cannot take y equals x line. You can take, right? It is according to the problem, right? Because in problem of the integral you need to according to integrals. Sometimes you need to integrate over y over x square, or sometimes you need to integrate y over x, right? I just not take this y of x line. It's just a straight line between joining these two lines, so I need to show the difference between the any arbitrary path. That's why I use y equal x square. Okay. So otherwise, there's no specific reason that I use y is equal x square, because I need to just to show the like difference between an arbitrary path, how we're going to do it in an arbitrary path. So that's why I'm taking y equal x square. Okay. So there's nothing more difference. So then if you take this line, so this what does this mean? If you take xy plane, right? Xy plane, if you take like x1 and might take x2, right? So let's say you have a y1 and you take y2. And in this case, what you're going to do? In this integral means that there's nothing more a line integral. This is an area integral. You're integrating over area. It means your y is going to y1 to y2. x1 goes to x1 to x2. You integrate over this area. Right? Now things get complicated. Okay? If you take the previous example, let's say if I take 0 to 1 and your x is always, let's say I go to 0 to 1 and would integrate 2x plus 1. Okay? dx dy. So how are you going to integrate this? So actually when you write this is actually this integral, we call this inner integral, right? This is inner. It means you should integrate it with respect to dx. Okay? And after integrating with respect to x, you will integrate it with respect to y. So you can actually integrate this, because if this in this case this limit are equal, so to be clear, I will put this as a 2, right? Just to be clear how it is. Also you can write this integrate like this. 0 to 1, 0 to 2, 2x plus y, and this in the case you will write dy over dx. Okay? Because the thing is, in this case, when you change this, interchange this variable, you should remember to interchange this limits as well. Okay? I think there is some certain delay in my screen. Where is it? Okay? So it means it means this inner integral, this integral is correspond to this dy variable, and this integral is correspond to this dx variable. Okay, so I think you can properly do it. So this integral is correspond to this x variable, and this integral is correspond to y variable. So when you integrate this thing, you can integrate. I will take the integral 0 to 1 and 0 to 2, 2x plus y dx dy. I can integrate this something like this, 0 to 2 and dy. I will integrate first 0 to 1, 2x plus 1 dx. When I integrate this, what will happen is when I integrate this my inner integral, this is called my inner integral, I treat this guy as a constant. Because when I integrate it with respect to x, it has nothing to do with my y. Okay? So all the variables are not relevant to this inner integral, I will treat as constant. So then I can evaluate this integral as 0 to 2. 2x, when you integrate this, you can write it is 2x squared over 2x squared. Integrate, when you integrate it is x squared, and you integrate with this to constant y plus 1, it means actually yx. It is just you integrate in your A levels just by treating y as a constant, and you will end up your limit 0 to 1 and dy. Now you end up with 0 to 2. It is 1 plus y. Okay. When you integrate your inner integral properly, there can be no x, no y. When you after you apply limit, there cannot be no more x in your resulting integral. Okay? Because if you integrate by x means you remove
your variable x from your integral by evaluating your inner integral. Then you can evaluate this thing. If you evaluate this thing, it is equal to 0 to 2. If you integrate 1, it is y. And if you get y square, y is evaluate, it is y square divided by 2, it is 0 to 2. You will get 2 plus 4 divided by 2, it is equal to 4. You get the point here? Is it clear? Or you need any other explanation? Hello? If you need any explanation?
Yes, it's clear.
Okay. Then you need to get, and also this triple integral is also the same, right? So you have something called this triple integral, let's say a to b, a1 to b1, a2 to b2, and a3 to b3. Then you have some fx, y, z, and dx, dy, dz. It means you first, it means this integral is correspond to your variable x, this integral is correspond to variable y, and this integral is correspond to variable z. Okay. So then what will happen is you first you integrate your inner integral, okay, this integral with respect to x, and then you evaluate. After evaluating this integral, with the result you will evaluate this integral with respect to y, and after that you will evaluate this whole integral with respect to z. After evaluate, you will end up with the real number. There can be no more x, no more y, or no more z at the final answer. Okay? You got my point clear? It's just easy, right? Okay? Hello? Fine? Hello?
Yes.
Okay. Okay. Now, let's say you have something like this. Let's say you have, if I take my function is fxy is something like this. Okay? Is equal to 2x plus 1. Okay? Now, you have to integrate this awkward shape. Right? Somebody is asking this question, actually I immediately forgot it. Right? Used to thank you and worship you. Because if this problem is come to an extent, I teach you because of you, right? Because otherwise they won't. Okay. Then you will get something like this. I will get to this y is equal to x square. Okay. Now we have to integrate over this area. Okay. Now you know how you evaluate this limit. Okay. So let's say I get an arbitrary point. Let's go. I move x from 0 to 1. That is fine. Now how is your y going to move? If you x going to move from 0 to 1, your y is going, let's say some arbitrary x here. Arbitrary x here. What is this going to? It's x squared, right? It is x squared. It means your x is going to move from 0 to 1. Your y is going to move from a particular x 0 to x squared. Okay? So then you can write your integral as something like this. 0 to x squared, 0 to 1. You put this limit first. Okay? 2x plus y dy dx. Remember, if you have some limit like this, let's say if your x goes from 0 to 1, and if you say any particular given x, your y moves from 0 to x square. It means this limit. Okay? If you have some limit like this, you have your variables have limited like this. These things should be inside the integral of x. Okay? You cannot write something like this, right? X square 0 to 1, 2x. This is the mistake you do in most probably in multi-integrals. You can write something like this. Because you cannot evaluate integral x inside because you have this variable x in your limits. Okay? So in this case, what you do is you move x from 0 to 1, and you check how is your variable y is going to move. Actually, variable of y, the range of y is depend on what is your x value is. Okay? If your x value is 0, your y is going to be 0 to 0. If your x value is going to be half, it means let's say x is going to be half, somewhere here, your y is going to move from 0 to 1/4. It means your range of y is dependent on your current x value. So it means you have to integrate x last, and depend on x you can put limits of y. Okay. So then you can put in the other way as well. If you send y from 0 to 1, right? If you send y from 0 to 1, then what is your x limit is? Let's say your arbitrary y value. Let's say some arbitrary y value here. Let's say this is some arbitrary y value. So what is the x value here? Your x value is corresponding root x, and your x is going from to root x to 1. Okay, because x is in here. Okay, you have to draw and see. If you have if they give you some awkward shape, you have to draw that shape first and then move one variable and then check, get some arbitrary variable. Let's say if you move x, get some arbitrary variable x. Let's now see how much your y is going to be, how much is y is going to behave with respect to your current x value, and then put it as a limit. Okay. So you can evaluate this integral as, you can evaluate this as, actually something like this. Let's say you can evaluate this integral as, you can evaluate 0 to 1 and dx, and you can evaluate this thing 2xy plus y squared divided by 2, it is 0 to x squared. Okay. So then you can have 0 to 1, 2x cubed plus x fourth divided by 2 dx. Right? So then you can evaluate simply as this. You can evaluate this thing as 2x4 divided by 4, okay, plus x5 divided by 10, 0 to 1. You can evaluate this integral as actually half times 1 over 10. You can evaluate this thing as 6 over 10. It is equal to 3 over 5. Okay. So you can easily evaluate, right? So you can easily evaluate this integral using the limit I choose to, because the thing is like, because you know the variation of y, the range of y is dependent on current value of x. Okay. If you move to 3D, what will happen? If you move to 3D, the same thing happens, right? If you move to 3D, let's say I just do the figure. Let's say x, y, z. So you can in a 3D, let's say you can have actually it is not coming to my mind first, right? So you can let's say something like this. We can write this to an integral somehow. It depends the shape you give, right? You can write fx, y, c, dc. Just say you can have this thing is something called some a1 to f, not some function of g. Let's say g1 of y and z. Okay, because okay, this is not dx dy. Dy dz. Okay. So then you can have this limit is y into some g2 z, function of z. Okay. So actually you can have this both limit if you want, right? If you want, you can have this both limits. Let's say you can have this say g1 yz, and this is g2 yz, and you can have h1 c, h2 c, and this only you can have only constant term. Okay. It means in this multi-integral terms, you can have this inner integral limits as a function of this outer integral variables function. Okay, let's say you have this, because you know this integral, let's say this integral is correspond to x, and this integral is correspond to y, and this integral is correspond to z. So when you choosing the limit for x, it can be a function of y and z, because these integrals are outside. Okay, but if we're choosing a limit for y, it can be only a function of z, because only z is outside. But if you choosing the limit for z, it should be a constant limit. Okay, otherwise you won't end up with a real number answer. Okay, fine. Actually, it depends how you get a shape, right? Because I cannot draw in 3D. Let's say you have something like how you going to draw it? Actually, if you have some equation of plane or something, it is some depend on how you get them, because it is some you have to imagine it 3D and draw. I cannot draw it, unfortunately. So you can easily get my point, right? If you say, let's say you have, let's say if your variable is right? If your variable is x, you in this case actually what you're going to do is actually you move your variable z, right? When you variable z, you see how your variables y is going to change. If your y is going to change in this direction, how is your variable x is going to change? Okay, so you need to check. Okay, so you need to derive some proper bound, and you can see how is your variables going to be changed. Okay, you move first z, and then you can get a bound for z, and then you say when your z and y values are fixed, how is your x variable is going to be changed. Okay, so you start from here. So from the outer integral, you move from because these limits are constant, so you identify the limit of one variable, and then see how this particular variable, let's say z takes a particular variable z naught, how is gonna y is going to be changed, and then you fix y naught and z naught in your range and see how is variable x going to be changed. Then you can get the bound for all of them. Okay, fine. Hello.
In the previous slide,
Okay.
the second double integral, can we write the limit as 0 to root y and 0 to 1?
Yeah, you can write. Also, you can write this as you need to write 0 to 1 and this 0 to root x. Okay. So no, not root x. This root this root y. Right? This root y. X because it is y equal x squared. No? It means x should be equal to root y. Okay. This should be 0 to root y, and then you can write FL2x plus y, and you should integrate with respect to x first and then y. Okay. Because you cannot integrate y first because what the your limit of x depend on y. Okay, fine.
Yes.
In this
Fine.
case, your limit of y depend on x. So then you need to integrate y first, then integrate with respect to x. Okay, fine.
Yes.
Okay, okay. So then actually the thing is same for triple integrals as well. So you can actually most of the time they will give you some integral respect to variable. Sometimes if they will give you integral respect to three variables, that's fine. You have to follow the same procedure, right? First you will choose what is, let's say you have some sort of cylinder, some sort of thing. Let's say you want to integrate in this in triple variables, you can get x, y, c, and you have some sort of cylinder kind of thing. You have to integrate inside this volume, right? This is actually this is d equals 0 plane and this is d equals h plane, right? And then you can have how you gonna be integrate this thing, right? So you know your zd is gonna be 0 to h. When your zd is gonna be somewhere here, why when you let's say this radius is 1, okay, this radius is 1, okay. So then in xy plane you can see something like this. Xy plane you can see a circle, right? So this radius is 1, okay. So your x is gonna be 0. Let's say your x is gonna be 0 to 1, right? Then your y is going to be what is your y? Because we know x squared plus y squared equals 1. Okay. When your x is going to be 0 to 1, okay, x is going to be 0 to 1 or 0 to 1, your y is going to be 0 to this thing is going to be 1 minus x squared square root, okay? 1 minus x squared square root. Your y is going to be, okay? In any of the cases, right? It is, and also if you take this line, this is minus 1 over x squared, right? So your x is going to be minus 1 to plus 1. So you can write this integral as this is going to be 0 to h. Your x is y is going to be your x is going to be 0 to 1. Okay. These are no limits because these are not a function of z. It is good, and then you can have 1 over x squared is 1 over x squared, and then you can have your function, whatever your function is. Right? You should integrate first dy first, and then dx, and this. Okay. So this is integral, right? Because this relates to your y and this relates to your x and this relates to your z. Okay, fine. Hello, fine. Hello, is that clear?
Yes.
Okay. Pull again. Somebody else if you can do ds first and then you can integrate this integral. Right? That is fine. You can integrate this integral. You can also write this integral as 0 to 1, 0 to 8, and this thing, this x guy, this variable t, and you can get some function, and you should put dy, dz, dx. That's fine because this integrals are not dependent on each other, right? Because this limit is independent of z, so you can change of this thing. That's correct. Okay, hope you get the answer. Hurry. Okay, so then. Yeah, you can also put something like the only criteria is like you can also write this integral as if you want, right? So 0h, you write, and then you can write 1 minus x squared and 1 minus x squared, and then you can write 0 to 1, and you can write fx, fy, fz, and you can write dz, dy, dx. The only reason is your integrand of dy should be inside the integrand of dx. The only thing is you need to remember that, let's say this is respect to y and this is to z and this is to x, your integral of x should be outer from the integral of y. Okay, that's the only condition. Actually, you can z you can put anywhere, right? You can put anywhere. The only condition is your integral of y should inside of integral of x because its limits containing x. Okay, it means you should integrate with x after you integrate with respect to y. Okay, such that condition is satisfied, you can put in any order of the integrations. Okay, fine. Okay, so the next thing is actually I need to give you an idea about how you change the what you call. Okay, somebody is unmute your mic.
අය මේ අරකේ x වල මේ වේරියේෂන බිඳුවේ ඉඳන් එක ගන්නයි ඍණ එකේ ඉඳන් ධන එක ගන්න නේද?
Oh, sorry. It should be minus one. Minus one. Okay, sorry. Okay, it should be this zero. It is okay because it should be going from here to here. Okay, so it should be somewhere. It is depend on a limit, right? So it is not nothing is just a limit. Okay? So the concept is the same, right? So I just know if you can see how to do it. Sometimes you will get some sphere or something, and then you need to. And if you get a sphere, the thing is getting more horrible, right? So if you get a sphere, something like this, a sphere means, and then you know the sphere is something like x square plus y square plus z square equals 1. Okay. So then how you going to do it? To one variable, you can send those from -1 to +1. Then your y is going to be, if you're -1 to +1, and then your y is going to be, let's say you need to understand how is your variable is going to be changed, right? X is going to be -1 to +1, and then your y and your z. So you need to understand how it's going to be your y is going to be, right? Let's say I think it should be going around something like y is going to be something like, if you take the proper diagonal, it should be, I think, go around, I'm not pretty much sure, it is 1 minus x squared to 1 minus x squared, as I suppose, right? Because it should be going the diagonal. If you get x and y, z should go around to, if in the middle, it should go as 1 minus x squared plus y squared minus times 1 minus x squared plus y squared. It should be plus. Okay, that should be the limit. Okay, because z is dependent on the variation of both. Okay, fine. Because if you're considering xy and you consider only the xy plane. Okay, so if in the xy plane it can go around to this, but if you go around to this thing, it means let's say now you write the integral, you should write something like this. Now you have no any choice, you have to put z inside, right? This thing. So let's say it is 1 minus this thing, right? You have to put z inside and this limit, and we have to put this limit, then y, and then you have to put x. So it is -1 to +1. So this go to az, and this to y, and this to x. So you can write your function and dz, dy, dx. Now you can't integrate, right? Because y's limit depend on x and z limit depend on both x and y. Okay, so you have we in properly ordered. Okay, fine. Hello, because it is only we use Cartesian coordinate, right? But if you use spherical coordinates, you can things get more simple. Because that's why usually to spheres we don't use Cartesian coordinates. Actually, this is very horrible thing, right? You cannot integrate in this form. Okay, fine. Hello. I just show how you get a limit. Okay, so then I will choose how you get interchange with polar coordinates, right? So then something like this. So okay, I would get polar coordinates, something like this. Let's say I would say the simplest form we know the polar coordinate, something like this, with the x and y. Let's say I get some coordinate on the x and y. Okay, some coordinate in Cartesian plane. I can write this as a polar coordinate by this length r and this angle theta. We know it, right? So then we can get this x angle is r cos theta, and this is equal to r sin theta. Okay, fine. So the problem is, right? So the problem is, okay. So the problem is when we move from here to here, okay. When we move from here, when we move from Cartesian coordinate to polar coordinates, our integral is become to fx y dx dy is become some f r theta. Okay, and we should replace our function with r and theta, and our integral become dr and d theta. But the thing is, we should scale this thing to match this. It means let's say what is now we will need know what this dx and dy means. Okay, which we call this thing an elementary area. And this is also an elementary area. If you properly do center of gravity in your A levels, you should probably remember that if you memorize, because in most of the time Sri Lanka will do it, just give the formulas and do not perform an integration at all, right? So just give the this is how it is proof, and if you ask why, it is the way it is. So it's the answer you should get. So that's why because that's why actually most of the time the lecturers are assuming that you are doing in this way A level, because in A levels in the center of gravity you have to get the elementary areas and elementary volumes and how these integrals perform under one variable, right? If you understand this concept in A levels, it's like a peanut, but unfortunately in Sri Lanka it doesn't happen because this is Sri Lanka. So actually this is a disaster, right? It's truly a disaster. So this is not your fault, right? It's not your fault. It's the fault of a country and our stupid, what you call the all of them, right? The senior people, because they have to they traditionally standardize these things, especially in education. Right? In Sri Lanka, there's no such qualification for education as well as politicians. Right? Like already the government teachers job is becoming like political appointment in recent years. Not I think far behind from like 10 years or so. There are teachers, and actually the most of the time the actual teachers are most of the time it's retired, right? So they are now is actually some I don't have to tell about, because if I don't tell about my language is pretty much bad, right? So I cannot tell about it. So the thing is like you need to convert this element to area. So let's say what the dx and dy means. Okay. Okay. So let's say I put some dx length, let's say dy length, and I get some dx length. This small area which we call dA or elementary area. It means when I move x a little bit and y a little bit, how much area can I cover in xy plane? But if when I go into Cartesian plane to let's say my polar coordinate plane. So now I have r and theta. How much area can I cover moving from r, little dr and d theta? This is my elementary area, right? Dr and d theta. How much area can I cover? It's pretty much clear. If you move from d theta here, it is dr. And if you move d theta, it is you change theta in this direction, right? If you move d theta, it means in this direction, d theta. Your change is you can model as it as a straight line or d theta, because the theta angle is very small. You can change the change of this angle. Let's say I do something like this. If you can properly do it, this angle is d theta, and you can think of it as this difference is as a straight line because theta is very small. Then this is the area you should cover, right? So this thing is become r d theta theta. Okay, this is the area you cover in polar coordinate. So instead of dr d theta, you should put r here. Okay. So actually, it is still drawing. Okay. Instead of dr d theta, you should put r here. This is why when you move from Cartesian coordinate to polar coordinates and also into polar spherical coordinates, spherical polar coordinates and cylindrical polar coordinates, you should have changed this variable because your elementary area should change. Okay, will change because in elementary area it's like a smaller rectangle in your Cartesian plane, but in polar coordinates when you move dr and d theta, the amount of area that you can cover will change with respect to the geometrical thing. Okay, fine. Hello.
Yes.
And then spherical polar coordinates, how are we going to do it? Actually, it is something like this. I will show you again. So if I say x, y, z, so it is always clear. If you can move from the z to this direction, and you can move the x, y to this direction, and you can move the x to this direction, you get a small cube, right? You get a smaller cube. So you got its elementary volume, right? You get elementary volume. But if you want to change this volume in spherical polar coordinates, actually my notation can be a little bit different, right? This thing, and you can get this angle, this shape. Okay. My notation can be a little bit different. You can later you can go with notate. So you can get this volume is how much you going to be changed with your dr, right? Your dr is going to be something in this direction. Okay. And your d theta is something is going to be this direction. Okay. and your d psi is something gonna inside this thing, right? This thing, right? This is gonna be something in this section. It's d psi. So this is actually r d theta, and this radius is actually r sine theta. This radius and this thing is r sine theta d psi. So you get the elementary volume. In this case, you get it is in other direction. You would get this elementary volume. You would get this dv. You would get dr times r d theta times r sine theta d theta. So r sine theta d psi. Okay. Then you would get r squared sine theta dr d theta d psi. So this term is coming out when you use spherical polar coordinates. Okay. So I will teach you some easier method to give you this thing if you moving from any arbitrary coordinate system to any polar coordinate system. So first of all, I need to in this point I need to clear that if you need to if you got the point that when I change from coordinate system, my what I call my elementary volumes, element areas will change according to the coordinate system. If you get that idea, it is enough for that movement, because I will explain how you exactly get this thing in the in explanation like in the very next moment. So if you have any problem with regarding to that, you can ask from there. Ask from here. Okay. Hello. Can you ask? If you have a problem, you can ask. Okay. Is there a problem? Oh, I will. Okay. Can go ahead. Occasion or something.
Can you explain the last part again?
This thing. Okay. So
Right.
actually, I will explain it's the vector valued function if you want, right? So let's say something like this. Let's say you know if you change your r a little bit, your position vector is go toward this direction. Is that clear? I think it is clear, right? When you are in this r a little bit, your position is going in this direction. That is clear. Fine.
Yes.
And then you increase the theta a little bit, your position is going to be in this direction. Okay. But if you in theta direction, right? If you increase the theta a little bit, because this radius is r, the length would be r d theta, right? Because if you have some circle, right? If you have some circle, this angle is d theta, this arc length is approximately equal to d r d theta. But since this d theta is very much small, we can consider as some straight line. Okay.
Okay.
And then if you increase psi a little bit, you go in this direction, but your radius is r sine theta, because this theta, because this radius is correspond to the psi. Okay. So it means it is pushed you at this point in this direction toward r sine theta d psi. Okay. Altogether, what you get? You get some like some cube like this. Okay. Some cube like this. You get some cube. You get some cube like this. Something like this. You get some cube like this. Your height is actually, let's say, you can put anything. R d theta, and your length is dr, and your width is, you can get r sine theta d psi. Okay, something like this. So your elementary volume is this thing. Okay, fine.
Okay. Okay.
So that's the way you find the areas and areas, something like this. Okay. So actually there's some easy way to do it. I will explain to you how you gonna be do it. So is that clear? Hello.
Yes.
Okay. So then how are you gonna do? So then actually so then you can do something like this. Then you can do, because you know now you can know, like say you can have some r theta, right? So rt, let's explain you something like this, xt and yt and zt. Okay. So then you put this r theta is somehow r10 r theta. Okay. You put something like this. Okay. Then to get this thing clear, you can get something like this. You can this r theta something. Then you get something like this. What you're gonna do is you differentiate this thing, because you say in them is r cos theta times r sin theta. Right? I would get something like this. Then I will evaluate dr over dr. Okay, dr over dr. Actually, it is like pretty weird thing, right? So let's call it rr, right? It's r's derivative with respect to r. It is actually sin theta times cos theta. Okay. And then you will get r derivative times theta. It is actually derivative which comes, you can get minus r sin theta times r
cos theta. So r cos theta. Okay. So then you can get the like the elementary volume something like this: r cross r theta magnitudes dr d theta. You can get something like this, and you can get this thing is you can get actually magnitude is something like this. You can get the evaluate if you get the cross product. You can get this thing is you can easily evaluate. This is the magnitude of this one, right? You can get the cross product. You can this is a vector, right? So this is actually if you get I j k, and you can get cross product is actually sine theta cos theta, it is 0, and you will get minus r sine theta, this cos theta, this 0, and you will end up times dr d theta. Okay. You will end up because you know that if you get respect to this and this cancelling out, you can only get respect to k component, right? It is actually sine. It is actually so it is this not this cos theta, right? The other way around. Cos theta sine theta. Okay. Because if you derivative with just 2r, it should be cos theta sine theta. You will end up with k times cos squared theta and minus this should be r here, right? This should be r here. So r cos squared theta, and you multiply this term, these two guys, it is minus r sine squared theta, and minus to minus sine, you will get plus r sine squared theta. This magnitude, right? This thing's magnitude dr d theta. You can clearly see this is equivalent to r times, because sine squared times plus cos squared theta is actually 1, and you would get r times dr d theta. And this is your elementary area with respect to your polar coordinates. Fine. And if you want to find the like let's say if you sine let's say some equal r theta and psi, you get some polar coordinate with respect to spherical polar coordinate with respect to like in your 3-dimensional space. You can calculate r, right? And you can get r theta, and you get r psi, and you will get to elementary area as r times r theta time dot product r psi times dr d theta d psi. You can easily perform on this. You can get r sine. You can get these r theta polar coordinates. You can easily get this vector using simple geometry. I'm not going to do in this, and you can get this thing. And I will show how this thing comes, right? That's what every time I do. If we say, let's say you have two vectors, right? You have two vectors. Okay. You have two vectors. Let's say A and B. If you know this parallelogram, what is the area of this parallelogram? You know from vectors, right? You know from vectors, right? You can find the area of a parallelogram using the vector calculus, right? What is the area? Area is actually A cross B is magnitude. Okay? Because if you know A cross B, you can write A's magnitude times B's magnitude times sine this sine theta times some vector normal to both of these vectors, right? Some vector. So if I take the magnitude, this normal vector is cancelling out. So what does this mean? Sine theta means me. This thing you can write, this height you can write A's magnitude times sine theta. So if you this angle you can write your perpendicular height A's magnitude times sine theta times B's magnitude. It is equivalent to the norm of your cross product. Okay. In the same way, you know using vectors. Okay. It is A, B, C. If you draw this this parallel, actually I don't know what is the term for this. It is some if you consider this like solid thing, right? It is a parallelogram or something. Actually, I don't know what is this thing. The term, right? I'm pretty bad with terminology. You can the volume of this thing, right? Volume. You can get this thing is from A cross B dot C, right? You can easily calculate because this thing is actually equal to A cross B times. You can write this thing as actually A magnitude times B magnitude times sine theta is this angle, right? It means already you can take this the area of this, okay? And you can write if you get the dot product, it means this with normal vector is with normal vector, and if you get dot product with this angle, let's say psi, and you will get C's magnitude times cos psi. The C cos psi is nothing but this perpendicular height. So you will end up with the volume of this object, right? So it means what does this mean? This thing what we do, we got our Cartesian plane, and we get how much your R is moving forward to with respect to our R and how much is going to be with respect to theta, and we get the cross product and we get the elementary area that we can cover, the parallelogram. Okay. In a three-dimensional case, we have another component R psi or something, and we calculate the volume of this small cube. That's what we're going to do. Okay. Fine. So you cannot do a geometrical figure. What you can do is you can get this, express this RT in terms of this, and you can easily calculate these two by differentiating it with R and theta, and you can get this thing to evaluate your integral. Okay. And also in three-dimensional case, you can easily calculate these three things, and you can easily calculate this thing, guys, to calculate your what you should do put inside of your dx, dy, and dz, your elementary volume. Okay. Fine. Hello. Is that clear?
Yes.
Okay. So that's it actually into the multivariate calculus part. So I have to, another part is actually in the divergence, curl, the curl and divergence and so on, the path integral, the closed loop integrals, and the thing in that case, so we need the ideas of the gradient and so on. So I think is it okay to done it today, or can we do it another day? I think if I do it that way, that will be too much for you, right? Because it will, you need to understand what is the gradient is, and then you need to understand how it's the gradient is varying and so on. So I can do it, that doesn't matter, but it will take some more another time like that, right? So then it will be some sort of like the tedious, like what you call like very much hard for you to sitting in front of a screen around, I think, another 1.5 to 1 hour. Okay. So is it okay? So can we continue another day? Actually, I will let you know. I think also I can. I think there are some videos on the gradient and so on, so you can probably watch them and come back, and then we can start from the what you call the Stokes theorems and Green theorems and so on. So what you do? Is that clear to all? I can actually do. I can do another around 1 hour or something. It doesn't matter. Come and do. Samath?
අය වෙන දවසක් කරා තව නෑ මම ෂේප් එක බලලා
Yeah, so you have to actually we have to note this because the thing is that the actually in the curl theorem is actually we have two integrals. There's a two theorems, so you need to know it is like curl and let's say this dA and on n, and then you can have divergence and dV. So evaluate this integral, you will need this, okay? Because anyway it will end up in like one in something on surface integral. The other thing is in volume integral. So evaluate these two integrals, you will need the theorems in this thing, right? Actually writing this thing is not much, right? Actually if you know understand what is the curl is and what is the divergence is, you can easily write away. But the problem is actually you can even memorize this, right? You don't need to understand what is the curl is, right? And what is the divergence is, right? You can memorize this, and the problem is to evaluate these two integrals. That is the way you face difficulty in the exams, and most of students fails, right? So, but I will because I can just say this curl is this and divergence is this and the gradient is this. I can do, but I will not do in that way, right? I will probably explain what is the gradient is and what is the curl is, and then you know what will happen. Because sometimes you cannot, some places are there, you cannot actually straight away apply these theorems, and you need to do some slight modification. If you just memorize it, you will miss those point, and you will lose entire marks for a problem. Okay. So that will happening. So that's it. So then we can wrap up in the session today. So we can arrange another day hopefully, and then we can do another session. I think hopefully, I think within this year or next year, because we have some time, we can take some time and arrange some time. Okay. Hello.
ඕකේ අයියා
සතුෂන්
Okay. Okay.
අර මේ අර 18 අයියලගේ බැච් එකට කරපු වීඩියෝස් ටික පොඩ්ඩක් දැම්මනම් හරිනේ ගෲප් දෙකට
Yeah.
අයියා
Yeah, in this case actually I will do in the 18 batch video. Actually it is a single video, so I will do I did in that the curl part and multivariate part, and also the curl divergence, and also I finished all the multivariate part, and also I did a little bit of complex analysis part. So but actually it is pretty much rushed, right? Because in the last Kuppi was done the 2 days before I tested positive for COVID, right? So I think that's how it's good. So I think that's why it is like little messy, right? So it's like I don't know what is in my body, but it's there. So then I think that the second copy is not much up to the standard, but I know it is. But it is good in to just to get some overview. So I will cover it for you guys. I think we can arrange another 1 or 2 sessions, so I can do. That's fine. So I will let you know the dates, but please let me know in advance so I can arrange some date, because in the last semester we don't have many lectures because some modules are not starting. So only our department modules are starting, so I have some time, so I can manage it. Anyway, this is my person, so I can manage.
අපිට එක්සෑම් එක තියෙන්නේ සෝෂානයි 21 කියලා
So
කිව්වා.
that's fine. Yeah, already.
19 වගේ ආයෙ කරමු.
Yeah, so that not 19, so we can do around first week of January 1 and second week of
ඒ
January 1.
දිගටම එක්සෑම්.
Okay, nice. Okay, so then if we can do it 19 also. Actually, I have one exam on 24th. So, actually, I didn't even look at the subject. So management module.
ඔයාට එක්සෑම් නැතින්නේ අවුලන්නේ.
No, it is a management module. That's the thing, right? It is not an engineering module.
අය ඕනම් මේ අයියා කිව්වාගේ 30 වගේ කරන්න වෙලේ තව සෙෂන් එකක්. කාටවත් එක්සෑම් එකේ
තියන පුළුවන් මේක මම පොඩ්ඩක් බලන්න මම තිය මොකද මගේ වැඩත් එක්ක බලන්න ඕනේ අපි FIP එකේ ප්‍රොජෙක්ට් එකක් ගන්න තියෙන රිපෝට් එක පොඩ්ඩක් එකත් එක්ක බලන්න ඕනේ මේක බලලා කියන්න අනිවාර්යෙන් මේ ලොකවුලක් නැහැ මට මේ ටික. ඒක ලෙක්චර්ස් මුකුත් නැහැ. ඉතින් මම මේ දවස් ටික ආතල්ලේ පොඩ්ඩක් රිසර්ච් එක කරගෙන පොඩ්ඩක් ආතල්ලේ ඉන්නවා. ඒක නිසා අවුලක් නැති මම හිතන් තියත් පැය කමාරක් වගේ නේ අවුලක් නැහැ. කොහමද මේක නිකන් ෂෝට් එකේ ඉතින් මම ගොඩක් එක දිගට පැය 4-5 දින්න නැතුව සාමාන්‍ය normally පැය එකමාරේ වගේ සිටින්න මොකද නැත්නම් වෙන්නේ මම ඔක්කොම එක දිගට කියන් යනවා. මට තේරෙනවා වෙනරුම් වලට තේරෙන්නේ. තේරෙන්නේ නැහැ නේ මොකද? එන පැය එකමාර දෙකර වගේ තියාගමු. දාලා ෂේප් එක කරගෙන. මේකෙන් මොකක් කර අවුල් තිබ්බනම් කියන අතර අපිට ඒක මේ මට ඕන නම් ආයි ප්‍රයිවට් මෙසේජ් එකක් දාන්න කිසිම ප්‍රශ්නයක් නැහැ. අතර හොඳට උනා කියලා හිතනවා මම හිතනවා කවර් කරගෙන ඕන විතරයි. ඇත්තටම මේකට හෙමින් කරේ. හරි මොකද කලින් එක ඕගොල්ලෝ බැලුවොත් මම මේ වෙලාවෙන් මම හිතන්නේ අනිත් පාර්ට්ටත් කරනවා ග්‍රේඩියන්ට් පාර්ට් එක. නමුත් අර ගොඩක් හෙමින් කරාද මොකද මේ අර ඔයගොල්ලෝගේ නිල් වෙලාම තියෙනවා කියපු නිසා. මොකද අතර මට අත්‍තර වේගින් කරන්න සිද්ධ වුණා ඒකේ මේ මොකද එක්සෑම් එකට දවස් දෙකයි තිබ්බේ මට කියනකොට. ඒක දවස් දෙකයි දවස් හතරක් වගේ තිබ්බේ. ඉතින් මට දවස් හතරෙන් කුප්පි ඒ සෙට් එකම ආවා කරන්න තිබ්බේ. ඒක නිසා සයිඩ් වේගින් කියනවා. තෝගලට කල් තියෙන නිසා අපි මීට ඔක්කොම ඩෙෆිනිට්ලි කවර් කරලා අර A+ එකට ලියන්න සෙට් එක. මේක ලේසි හරි මේක තේරුම් ගත්ත කෙනා උඹට ඇත්තටම කර්ල් එකයි ඩයිවර්ජන්ට් එක නැහැ ආයෙක නිකන් මතක තියාගෙන ලියන්න පුළුවන්. නමුත් අර මේක අයිඩියා එකම පැහැදිලි කරලා දෙන්න. ඕකේ. හෙලෝ.
thank you
Okay.
thank you
Thank you සෝෂානයි.